Hi there, students. Welcome back to this channel. Now, I'm excited to show you this video because in this video, we are going to be learning about the magnetic effect of current. Now, of course, in order to understand the magnetic effect of current, we must first know what magnets are generally, or what a magnet is basically. And the reason for that is because it helps us to understand the historical development of the understanding of magnets. Now it came to being used, or it got to be known that it was connected with electricity. Yeah, because the early users of magnets were not very familiar with the fact that they didn't know that magnets was connected with electricity until 1820, of course, when Hans Christian Ørsted, a Danish scientist, proved that in his science experiment. Now, in this video, I'm going to be showing you first the historical development of this knowledge. Now, it's usually very important to learn it from the scratch so that, because knowledge add up. Is that okay? So that the knowledge will add up and it will make sense from the scratch where it started from. All right. So if you are a lazy student, of course, click out of this video. But if you're not, and you're ready to learn this topic of magnetism, stick with me till the end of this video because I promise you by the grace of God, you are going to get everything that I'm going to say and it's going to make sense to your passing, make sense to you, and it's going to help to pass your exams. And of course, you will not regret that you clicked on this video. All right, let's go on. Now, we're going to be starting with the history of magnetism. Now, let's rewind. So join me as I rewind back to 2,500 years ago, all right, about some 200 BC, when a certain shepherd, now this story is not exactly what is generally acceptable, but that is what I've heard from many people now. And so a certain shepherd was going in the wilderness with a staff that was metallic. Now that metallic staff, one of the days he was, in the wilderness with his sheep, got stuck to a rock. And as it pulled, it kept seeming like it would not go off of that rock. Like the rock was drawing the metal to itself, and he was trying to draw it off, and he couldn't. All right, so this was the discovery of this special stone that would later be known as lodestone. Now, where was this event taking place? This event was taking place in Magnesia. That was then in Asia Minor. Asia Minor. That is China. China. So it therefore presupposes that the earliest users of magnets were what? The Chinese. Yes, the Chinese were the earliest users of magnets. And the reason why it was named lodestone was this. Lodestone means leading stone. Leading stone. This was because the first practical use of the lodestone or magnets was to navigate the sea. Is that okay? Mariners used it to navigate the sea. And of course, that is why it was first used in the construction of a compass to tell the locations on the earth. And how did we come about that? Soon we will know that in the 17th century, an American physicist named William Gilbert came up with the proposition or propounded the fact that the earth was actually a gigantic magnet, a big, huge magnet. So, and that was why it was possible to use a magnet for a compass. This was because it was noticed then that when a magnet, you can also try it. Now, if this was a bar magnet, now, if this guy with me was a bar magnet, now if you suspend it freely, this bar, if it was a magnet, it would come to rest freely in the roughly north-south direction. So, and that was the way a magnet generally behaved. So, for this reason, it was known that it was used for what? Navigation. That was the earliest use of magnet. Okay, so this is the short history of magnet. Now, the lodestone was found to be what we now know as magnetite, which is an ore of iron. You know, we have many ores of iron. We have hematite, we have magnetite, and it has the formula. So lodestone is a magnetite, and it has the chemical formula Fe3O4. And they should not be confused with Fe2O3. This is rusted iron. From FeO becomes rusted, that it becomes oxidized and becomes this. So this is rusted iron. This is magnetite, Fe3O4. All right. Now, where are we heading to now? So, what is a magnet itself? Now, a magnet is a substance that can attract pieces of metals to itself when naturally or when current is passed through it, and that is why we want to study the magnetic effect of current. What current? How current can make a substance magnetic. Is that okay? All right. So we said the magnet is a substance that does what? Attract pieces of metals to itself naturally, either naturally or what? When current is passed through it. And that will bring us to the types of magnets. The types of magnets. Now there are two types of magnets. A magnet is either natural or a magnet is artificial, of course. Now a magnet is natural if, without passing current or anything to it, it can attract pieces of magnet to itself. An example is the lodestone. So lodestone is a natural magnet. But artificial magnets are the ones that require the passage of electricity. So it requires current being passed through it before it can display any magnetic property. And an example is iron, soft iron, steel, and all of these other nickel, cobalt. So they are all artificial magnets. So we said this one, lodestone, and we said the artificial magnet is the iron, we have nickel, we have ferromagnetic materials basically, steel, cobalt, etc. So these are what? These are ferromagnetic material, and I'm going to get into that in a jiffy. But these are ferromagnetic material which are what? Can be made into artificial magnets. And there are different types of artificial magnets. There are some that are temporarily magnetic, and there are some that are permanently magnetic. So we have two types of magnets under the artificial magnets. We have temporary magnets and what? Permanent magnets. Now, before we get into that, okay, let's already get into that. Now, there are two types of artificial magnets. We have the what? The temporary magnet and the permanent magnet. So, for example, for soft iron, when you try to magnetize soft iron, it magnetizes easily. Soft iron magnetizes easily. So, and because it magnetizes easily, it can also be demagnetized easily. So, it is made into what? A temporary magnet. Any material that can be magnetized easily as well as demagnetized easily. The ease of magnetization is equal to the ease of demagnetization generally. So if it can be magnetized easily, it can also be demagnetized easily. And they are what? Temporary magnets. And some of where we use them are our earpiece, our doorbell. Those are things that require soft. They require only temporary magnetism, temporary form of magnet to work. So we call them what? Temporary magnets. While substances like nickel or steel are permanent magnets because number one, it takes time to get them magnetized and they retain their magnetic property for long. So example is steel. Steel retains its magnetic property for long. All right. Now let us get into some terms that are used in magnetism. So the first itself is magnetism. Now what is magnetism? Magnetism. Now magnetism is the ability of a substance to attract pieces of magnet of iron or metallic materials to itself. That is what you call magnetism. All right. Now, and we have magnetic material. Now, a magnetic material is a substance. A magnetic material are basically called ferromagnetic. Are basically referred to as ferromagnetic. Ferromagnetic. Now, based on based on the effect of magnets on metals, we know, or the reaction of substances to magnets, we classify all substances on Earth into three based on their magnetic property. And that is number one, we have ferromagnetic materials, we have diamagnetic materials, and we have paramagnetic material. Now, the ferromagnetic materials are the ones that are easily magnetized. It means that by themselves, they easily get magnetized onto a magnet, while a diamagnetic material are the ones that are unaffected by a magnet. Then the paramagnetic, in fact, you see the word ferro means iron. In fact, the word iron, you discover that iron is given the symbol Fe because the Latin word from which it was coined is ferrum. So ferromagnetic means iron, ferromagnetic, all right? Then para means weak. Para means weak, weakly magnetic. So they get weakly deflected towards a magnetic field. Why a diamagnetic material, in fact, will be repelled or will be pushed away by a magnetic field. All right. Now, these are the characteristics of, the classification of things according to their magnetic effect. And we're going to still get into it when we see what we call the magnetic domain. The magnetic domain. So we have talked about this. Now let's talk about the magnetic pole. The magnetic poles, or the parts of the magnet. Now, first, there are two shapes or two forms in which magnets exist. We have the bar magnet, the one that is bar-shaped, and we have the horseshoe magnet. For the purpose of this video, we are going to be talking about the bar magnet a lot. Is that okay? Because it's easier to comprehend and easier to use. Of course, they are both magnets. Now, a bar magnet is just a bar. Looks like a bar, and it's basically a bar. So, now, in a magnet, typically, we have what we call poles, magnetic poles. Just like we have in electricity, we talked about a positive pole, a positive charge, and a negative charge. We also have two end poles here, and we call them the North Pole and the South Pole. Now, the North Pole is the pole that looks like the positive pole. Now, you remember that in electricity, we talked about the fact that the positive charge is the one that the electric force acts like it's emanating outwards, going outward from. So the same way, the North Pole, just like the positive pole, the positive charge is the one from which the magnetic field flows out, while the South Pole is the one in which the magnetic field flows in from. Is that clear? All right. We are still going to build more on that, but that is just me showing you how they relate with electricity a little bit. Now, these are the poles, and the magnetic pole is where its magnetic force is strongest. So, if these magnets were to be thrown in a jar containing iron filings are if you scrape iron, if you scraped it, if you've ever been to where they grind maybe sharpen cutlass, sharpen metals generally. So you're going to see some filings on the floor. So those are filings to the iron, if that material is iron. So we call them iron filings. So if you throw a magnet in that place, you're going to see that tiny piece of materials will be attracted more to the poles. more to the poles because the magnetic field, the magnetic force is strongest at the poles. We will soon know why, but let me give you a hint of why. Now, the density of what do we use to represent the magnetic force? Remember the electric force, the electric field lines, right? Okay. Now, the magnetic field lines also are densest or are closest together. And recall that the closer they are, or the higher the density, the higher the what? The force. So the higher the density here, the high density here causes the magnetic force to be what? Higher on this both sides. Does that make sense? All right. Now, before we get to magnetic field itself, let's quickly consider the properties of a magnet. The properties of a magnet. Properties or characteristics, basically, of magnets. Now, the first one is that it has two poles. It has what? Two poles. Now, a magnet never has one pole, as in there is no magnetic monopole. No magnetic monopole. So what that means essentially is this. Now, if I had my magnet like this, my back magnet like this, now I have my north and south. If I broke this into two, now you might be expecting that I had one side here north and one side here south. But no, what automatically happens once this is broken is that a new dipole is developed. A new dipole is developed. I decide to break this into two again. I develop a new dipole again, even in the tiniest bit of magnet that I cut this into. I always have what? A magnetic dipole, no magnetic monopole. Good. Now let's go to the next thing. So we have what? Two poles. The second thing is that opposite pole attracts. Like poles repel, and unlike or opposite poles attract. So you will see that this is similar to the law of Benjamin Franklin, that like charges repel and unlike charges attract. Here also we say that what like poles repel and unlike poles attract. All right. Now, this is what that means. If I had a magnet like this and I had north and south here, if I put another magnet beside it and it had north and south, and basically this must be magnets. Because if this was not magnetic, if it was not magnet, but it was a magnetic material, they will attract each other because of what is called magnetic induction. Basically what I'm going to explain after now. So, but if this was a magnet and I brought this magnet and I brought the south to face this south. Now here's what will happen. They are going to repel each other. They are going to push apart. They are going to push apart. So, and I'm going to explain how that happens with the magnetic field. Now, notice how I said that magnetic field always enter from the south, just like it enters in electric negative charge. So, magnetic field always enter at the south. So let me draw this well, a little far away from it. So we have here. So magnetic field always enter at the south. So if it enters here at the south, enters here at the south, enters at the south. Now they never cross each other. Is that okay? If it enters at the south, what do you see? This is arrow coming like this, an arrow coming in like this, coming in like this, going in, going in, going in, and going in. So you see that these arrows are going to push apart. So there's going to be a point here that we'll call the neutral point. So the neutral point is the point of zero magnetic force. The neutral point is the point of zero magnetic force. We're going to see it further better when we see the Earth magnetic field. So that is why it's pushed apart, all right, or pushes apart. Now, what if I now brought the same magnet? I have the north-south here. I decide to turn this one into the north-south direction. Here's what will happen. You are going to see an attractive force. An attractive force. This is going to be attracted to that guy, and that guy is going to attract to this guy. How does that happen? Remember also the same principle the magnetic field always flows inside at the south, enters through the south, and goes out through the north. So this is going out through the north. It's going out through the north. So what do you see? The arrows are what? Agreeing in terms of what? Position. You are going to understand this when we get to magnetic domain. They agree in terms of position. So because of that, what this basically turns into is that you are going to see magnetic field proceeding from north to south, entering the south and coming out of the north. And then there is an attractive force. All right. The same thing happens if it was north and north for this one. It was north and north, they're going to repel apart or push apart. All right. So what did we say? We said, well, like poles repel, while unlike poles attract each other. Now, number 3, another property of the magnet is that the magnet always induces magnetism of a magnetic material before attraction. This is what I'm saying. That if you brought a piece of metal, so we call that property magnetic induction. If you brought a piece of magnet close to a magnetic material, a ferromagnetic material, so a material or metal that can be magnetized, here's what will happen. So this guy is our magnet. This guy is not a magnet, but a metal that can be magnetized. So what happens is this: once you bring this magnet close to it, what happens before magnetization is magnetic induction. So we say magnetic induction precedes magnetization. So before this guy can be attracted to it, this guy has to immediately first be turned into a magnet. So to be turned into a magnet, so before that guy can attract it. So this is what it does. Once it is brought close to it, it induces opposite polarity on this guy. And by opposite polarity, I mean that if this guy that was brought to it were south, as we are seeing, is going to induce the opposite polarity on here, so that the opposite polarity is induced on this side too. Do you understand? So that is how what magnetization then takes place. So we say what? Magnetic induction precedes what? Magnetization. Magnetic induction before magnetization. Good. That piece of metal temporarily becomes a magnet before it becomes magnetized. Before it becomes magnetized. Now, another property of magnet that you should see is that magnets always have a magnetic field lines around it. It has a magnetic field that we call the B field. There is a magnetic field around it. Magnetic field around it. So let's talk about the magnetic field of a magnet. Let's talk about the B field, basically. Call it the B field. Now, one thing you should know about now, see an arrow on top, it means what is a vector. And that is very, very important for you to know. Magnetic field is a vector. Now, let's see this. So what that idea is basically talking about is that if I had a magnet like this is my bar magnet. There is a magnetic field that is around this magnet all of the times, and that is why it is able to attract substances to itself. So what is happening is this. We said the magnetic field always goes out from the north. So this is where it goes. It always goes out from the north, enters the south. Out of the north, enters the south. Out of the north, enters the south. Out of the enters the south. Do you get that? All right. So it's going to go out of the north, enters the south. Out of the north, enter 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 the south. Always out of the north and always enters the south. Now keep in mind that these lines do not cross. These lines do not cross. They do not cross. We are going to notice something. Now, the more they move far away from the poles, the more dispersed they are. So as they are dispersed, their magnetic effect or magnetic force reduces. So the denser the magnetic field lines, the higher the magnetic force. So the strongest magnetic force here will be felt where? In these two regions, which are the poles. That is why you see an iron furnace have those ions filings more at the poles than at the edges, because the magnetic force is more concentrated at the poles than at the area of the body. Do you understand that? All right. So some of the let's now talk about the the characteristics or the properties of these magnetic field lines. Is this now B field lines? Number one is that they go out from north, out at north, and in at south. Now, number two is that they never cross, just like electric field. Never what? Cross each other. If they were to cross, they will create a neutral point. Is that okay? They will create a neutral point, and at the neutral point, what happens? There is no magnetic force. All right, so because of that, they do not cross. Now, number three is that now this is what separates the magnetic field from the electric field. The magnetic field is continuous. B field is continuous. Remember I told you that there was no magnetic monopole. This is the reason. Now you remember that in an electric field, we will have something like this. The electric field will go out like this, go out like this, go out like this, go out like this. Every time it goes from positive to negative, everywhere. It goes out at positive and enters at negative, everywhere. But it's quite different it's quite different in the magnet. Here's what happened in the magnet. So as it is coming out of the north here and entering the south here, it is going back to the north inside the magnet. So magnetic field, so if you are asked, in what direction the magnetic field flow, you should ask where. Is it inside the magnet or outside the magnet? Because now you can see that inside the magnet, magnetic field goes from south to north. Do not forget that. Inside the magnet, magnetic field goes from south to north. But outside the magnet, magnetic field goes from north to south. And this property, this thing I just said, is very important for you to understand how a solenoid works. Because you might see questions where you are asked to tell the direction of the north, or the direction where will be the north and where will be the south when we begin to talk about magnetization and electrical method of magnetization. So inside the magnet, so this is the reason why it is continuous, because you can see it's a continuum from north to south, from south to north, from north to south. So it's a continuum. The magnetic field lines are what? They are continuous, unlike electric field lines. That's why we can have what? A point charge, but not a point pole. Does that make sense to you? All right. The lines are continuous in B field. The lines are they are discontinuous in the electric field. And that's what separates them apart. So, but they also are, when we talked about this thing, if I put two parallel magnets together, and this were to be the south, this was the north, and this was the south, you already see that the magnetic field will be straight towards the what? The south, from the north to the south. But at their edges will be radial. Is that okay? There will be curves there. Curves. So just like the electric field is also. Okay. Now, let's talk about what we call the magnetic domains. Magnetic domain. I'm going to clean this property of magnet. Magnetic domain. I'm still coming back to this. Now, magnetic domains the best way to think of them, magnetic domains, the best way to think of them is that they are atomic magnets. They are atomic magnets. Now see this. So in any property, in any material, every material has its own magnetic domain. Is that okay? So for example, in this marker is plastic, so it has its own magnetic domain, and the magnetic domain are not well assembled. That is why it cannot be magnetized. So the magnetizability of a substance is dependent on the organization of its magnetic domain. Or let me put that in form, better form. So if I have a metal plate like this, now these metal plates, because it is metallic, we have a well-structured or organized magnetic domain. So you are going to see that the teeny tiny magnet now, this is not atomic, is that okay? I'm just trying to show you. So if I zoomed into the atoms, this is what you will see, that the magnetic foil metallic guy, they just section themselves. They, put themselves together into different orders. And each of those parts, you will notice that the arrows are facing exactly the same face, the same direction. So that is to show you that they are what? Organized. And this degree of organization is what makes the metal to be magnetized. Substances that are not magnetized. So look at this other substance. This is another plate, maybe plastic. Now, what did you notice here? The magnetic domain are in disorder here. So because they are in disorder here, it will take a lot of, in fact, they cannot be magnetized. That's just the thing. They cannot be magnetized. Unlike, look at these guys, the magnetic domains are almost, they are all in the same direction. So this kind of guy is going to be a strong magnet, number one, because the degree of orderliness in the magnetic domain too, if all the magnetic domain are facing a direction, that is when you have a very strong magnet. So the magnetic domain is just the orderliness of the atomic magnets in it, how the magnetic field flows inside. So you see what that means here now, that it always goes from here to here. So in this case, we have what? Inside the magnet, it's always going from what? South to what? To north. Inside the magnet, always going from south to north. So they arrange themselves in this direction such that what you will now have will be a north pole here and a south pole here. So, but of course, they are atomic, right? So adjacent poles will cancel out each other so that everything can now align in the same direction, and we have only one south pole and only one north pole, so that the energy is concentrated at the ends. Do you understand that? And that's what we mean by what? By magnetic domains. Now, let's come back to this. So for ferromagnetic material, they have a highly organized magnetic domain. Therefore, a paramagnetic material, they have a fairly relatively organized magnetic domain. Relatively organized magnetic domain. So you can see this, some are pointing this direction actually, while some are pointing roughly upward, roughly downward, and but not all of it are disorganized. Unlike this one, look at this one, everyone is haphazard. So this will be a diamagnetic material, this will be a paramagnetic material, and this will represent the magnetic domain of a ferromagnetic material. All right. So now let's go into magnetization and its method. Now, so far so good. If you have enjoyed the video, do well to like and comment. Is that okay? If there's any part of it that you have not understood too, make sure you put it in the comment section. I'm going to check and still respond to you. Or you can always reach me on my WhatsApp number, +234 +2349021416307. All right, let's go. Now, we want to talk about magnetization, methods of magnetization and demagnetization. Magnetization. All right. Now, the first method of magnetization is the mechanical method. Now, the mechanical method. Now, by mechanical method, it means that you have to put in the work by yourself, right? So, we have the first type of mechanical method is what we call the single stroke. We call it mechanical method or stroking method. Stroking or touching. Is that okay? All right. Now, we have the two types of stroking. We have the single stroke method. Now, the single stroke method is this. By magnetization first, we mean that we want to turn something that was not a magnet before, we want to turn it into a magnet. So now we have the single stroke. The single stroke is this. We are going to put a magnet. So let's say these were my magnets. These were what I wanted to make into a magnet. This is what I want to make into a magnet. And this one is magnet. This green marker is magnet. This black marker is not a magnet. Now you see. So what I want to do is this. If this was my north, this head north, this bottom south. Now I'll take this my magnet. I will now stroke in one direction. Now it will make you understand why we study magnetic domain now. Now, provided that this guy can be magnetized, it has to be ferromagnetic. Is that okay? Good. So I'll take my magnet and I'll begin to stroke. And notice my motion of stroking. You bring it down from one end to the other. Then when you get to the next end, you lift it up and go back to that direction and go again. Lift it up, go back to that direction. You always lift it high when you get here. This is the reason. What you are doing by stroking is that you are organizing the magnetic domains so that they can point in the same direction. So why you have to lift it up at this point is that if you bring it back like this, some of the domains will shift again to that direction. Do you understand? So you have to bring it, you take it in one direction, lift it up, so that the magnetic field would have, the magnetic field cannot affect this point again. So you bring it here down again, then you use the magnetic field of this magnet, to stroke in this direction, organize the magnetic domain towards here, lift it high again, stroke in that direction, and stroke in that direction. Is that okay? Now, this is what happens. The point where you stroke towards, so if I stroke in this direction, this point where I lift it up will get the opposite polarity of this point. While the point where I'm starting from to stroke is going to get the polarity of this magnet, of this point here. So this is what I mean. So I have my piece of metal here that I want to stroke, I want to make into a magnet. And I take my magnet, so this is not a magnet. And I take my bar magnet. So I take my bar magnet, and this could be my north. I decide to stroke with the south. Now by stroking with the south, you're going to bring it here, lift it up, take it back. Bring it here in this direction, lift it up, and take it back in this direction. That's how I'll keep going for a while until this guy has become what? Magnetized. So this is what will happen. This point where I started this guy is going to get the polarity of this point, and this point, this guy is going to get the opposite polarity. And that is how the single stroke technique works. Give me that marker. Give me that second marker. All right, let's go. Now, the double stroke technique. Where's it? Now, the second type is the double stroke technique. The double stroke technique. Now, in the double stroke technique, you have two magnets to stroke with. You are still stroking a bar, but this time you are using two magnets to stroke one bar. Two magnets to stroke one bar. So let's say you decide to stroke with this end and decide to stroke with this other end. One thing you will keep in mind first is this, that if you stroke with south here, where you lift it away from, always get the opposite polarity. You see? Do you understand? So this point, this second magnet has to go what here? North. So that this point will get the opposite polarity. That's just one thing you should know. You stroke in the same manner. You go like this. Do you understand? So as you're stroking this way, let's say this way my magnet. This one is this is the head of the magnet. Okay, yeah. I have two identical markers here. So these portions here are north-north, south-south. So I come like this. I can't put north-north together here. I put north-south, then I stroke like this and lift it up, then bring it back again, stroke again, lift it up. The essence of lifting it, I told you, is because I don't want to disorganize the magnetic domain. If I were to do like this, and I'm just bringing it back, as I'm bringing my hand back, some of the magnetic domains will shift again and get disorganized. And remember, what we are trying to do in magnetization is that we're trying to organize the magnetic domains of that magnet. All right, so by double stroking, we have this. So what would now happen if you were to stroke with north-north? I mean, you know, this would be the south of this. This would be the south of this, would be south and north of this. So if you were to stroke with north-north, what would happen? Now you will result in what we call consequent poles. Consequent poles. I mean, south-south. That's a consequent pole. And this thing is not a magnet. Do you understand that? All right. Let's go to the next thing, which is the... Okay, so we've done mechanical stroking. Mechanical method. Now, the second mechanical method is called hammering. The second mechanical method. So the first one is stroking. The second one is called hammering. Now, this is one of the oldest technique of turning a substance, a magnetic material, into a magnet. So you take a bar magnet, for example, and heat it until it is red hot. So when it's red hot, you now hammer it along the north-south direction. Once you hammer it along the north-south direction, what will happen is that the magnetic domains will shift. So what you first did was to heat it, right? The reason why you heat it is what? Is to break the bonds or free the magnetic domain. After freeing the magnetic domain, everything will now be easy. It will not be easy for it to what's it called? For something to it will now yield. Do you understand? So it will now yield to that magnet. So as you're hammering it in that direction, you are still vibrating it so that the atomic magnets, which are the magnetic domains, can align itself in that north-south direction. All right. Then the next type of magnetization, which is also, okay, this one is electrical, that's number 3. And this is the most effective part, effective method of magnetization, electrical method. Now, this is what you do with an electrical method. First, you must know what is called a solenoid. Now, a solenoid is basically a piece of metal around which you tie metal wire. You tie a wire, rather. You tie a wire. So this is what you do. This is the setup. Let's say I wanted to magnetize this piece of metal, this bar. So what I'll do is I will connect wires to a battery. Now what I'm going to be using is a direct current. To magnetize, we use what? A direct current. Because to demagnetize, we use an alternating current. Does that make sense to you? To magnetize, we use a direct current. To demagnetize, we use what? An alternating current. All right. So this is it. We'll come here, we'll connect our conductors, and the conductor, which is your wire, will now be connected like this. Notice how I'm taking care to draw it well, so that you understand what is happening here. So what I basically did is to put my wire around it in this direction. So the way I'm going is like this. You understand? So look at the motion of my hand. I'm going. So I went like this from this side. I'm going like this. So it's only this front that you can see. Is that okay? And here this is positive and negative. Is that okay? And remember, conventional current flows from positive to negative. So since conventional current flows from positive to negative, here it go like this. Here current will flow like this. Here current will flow down. Here current will flow up. Does that make sense? So at the back, current is flowing up. Outside here, current is flowing down. 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 All right. Now listen. I'm going to teach you 2 tricks To understand where will be the north of this guy. Where will be the north. Now, at the back, there is a rule called the first right-hand rule. That's what we're going to discuss next after this introduction to magnetism. So the first right-hand rule is what helps us to know when current is passing through a conductor. As current is passing through a conductor, that conductor has magnetic field surrounding it. And this is where we know it. If this were to be your conductor, this thing, let's say this is your conductor here. Your conductor is a wire. So if you wrap your hand around it, if you set the current to flow like this, upward in this direction, it means that the direction of the magnetic field is the direction in which your hand curls around it. The direction in which your hand does what? Curls around it. So it means that at this point, magnetic field is into the board. I'm going to teach us this later. Into the board and outside of the board. Into the board, out of the board. Into the board, out of the board. As well as at the back. But here, current is going down. So we're going to turn our hand so that this thumb will go to the direction of, as I said, thumb is going in the direction of current. So that's why we say that this one is into the board, outside the board. Here, current is going in the direction of, yes, this thumb is going in the direction of the current, so current is flowing down. So we put it down, and then you're going to see that the magnetic field is like this. At this side is going like this, and outside is coming like this. Is that okay? So on the magnet, magnetic field is going like this, and outside is coming like this. So magnetic field is going like this. Does that make sense? Magnetic field is going like this. At the top, you can also examine that at the top, since your current will be going outside of the board, magnetic field will be going like this. Like this. So notice that outside, magnetic field is going like this. Is that okay? Outside is always going like this. If you don't understand this, don't worry, I'll still explain later in the next video. So don't click off yet. Is that okay? Alright, another way to view it is this. Another way to view is this. Okay, from with what I just explained, for those of you that understand, it means that if you say that current is going outside, if it is always coming like this and going outside like this, and entering like this, so it means that this place will be our south, and this will be our north of that bar when we are done. Because inside the magnet, it will always go like this, from south to north. So if you notice, it's going from south to north. Do you understand now? It's going from south to north. All right. Another way to view it is this. Now, to know the north and south, if you stand at this point, where is current going to? If you stand at this point, this side I am, relative to this guy, current will seem as if it was flowing in the clockwise direction, clockwise. So the direction where you stay to see the current flowing clockwise direction will be your south. While the direction where you stay to see the current flowing in the anti-clockwise direction is your south. I hope you put that down. So you see it is your north rather, north. So if you stay here, you see that the current is flowing in the anti-clockwise direction. Anti-clockwise, counterclockwise. We call it the north side. Does that make sense? Does that make sense? So these are the three methods by which we magnetize. Mechanical stroking, demagnetization by hammering, magnetization by hammering, and the electrical method of magnetization. So how do we now demagnetize? It is almost the same principle. We use the electrical method for demagnetization. So all you have to do is this. Pass current through a solenoid. Pass current through a solenoid using an AC. So if you pass alternating current through a solenoid, and then you now withdraw it far, gently, far away, and you're passing the alternating current. What will happen now? The reason why we pass direct current is what direct current flows in one direction. So if you use one direction to be organizing the magnetic domain of that material in one direction. Do you understand that? But if you pass an alternating current, if you pass an alternating current through a solenoid, if you pass an alternating current through a solenoid, so the current will be flowing in up, you know, it will be going forth and back, forth and back. So because of that, it will disorganize the magnetic domain, and then that material will be demagnetized. And notice that when I told you that steel is used for permanent magnets, and this is the best method of magnetization and also the best method of demagnetization, electrical method. The second method of demagnetization is, of course, hammering. If you hammer a, a magnet or a bar magnet, you hammer it for too long at the east-west direction, you demagnetize it. Another way is if you hit, the second one is, so we said method of demagnetization electrical. By electrical, we pass what? Alternating current. The second one we said hammering. In hammering, we said just hammer the stuff at the magnet at east-west direction. Then we now said for this guy, for the electrical method, remember that I said that you're going to withdraw it gently far away. Right. Then hammering. So we said heating. So when you heat a magnet till it's red hot, you demagnetize the magnet. All right. Those are the three methods of demagnetization. And of course, I said electrical method is the most effective. All right, before we call it a day here in this first video, because I'm going to go into the second thing. Now, let's talk about what we call magnetic shielding. Magnetic shielding. Now, magnetic shielding is this. You are trying to prevent a substance from being affected by a magnetic field. So, for example, we have things like MRI scanners. Now, MRI scanners are usually affected by magnetic field. So, because of that, you have to put them in a metallic casing so that this is what will happen. The magnetic field, so this is how magnetic shielding occurs actually. So, you know that a soft iron is easily magnetized. So because of that, if you put a magnet beside it, close to it, what will happen is that it will cause the magnetic field to flow in a particular direction. So on the other hand, it will flow in a particular direction. Remember, they don't cross. I'm just trying to show you what happens. So these are magnets and these are magnets. So it will cause. So this space here is the place where you have shielded. So you have shielded this space, so the MRI scanner can stay here. So and because of that, it will not be affected by what? Magnetic field. So basically, magnetic shielding is when you prevent something from being affected by magnetic field by putting a metallic core, an iron core, to separate the magnetic field, right? To prevent it from reaching a place. The magnetic field cannot pass through this point. That's the point. Magnetic field cannot pass through this place, so you have protected this point. All right. Another thing we'll talk about is the magnetic keepers. Magnetic keepers are basically metals that prevent, for example, you know that we've said that soft iron is easily magnetized and easily demagnetized. So the magnetic keeper is one thing you can use to prevent it from losing its magnetic property naturally. So how does it work? You place two bar magnets made of iron, iron Fe. So you place them with opposite poles, and then you now use magnetic keepers to protect them from losing their magnetization. So these are the magnetic keepers. These are the keepers here. It prevents them from losing their magnetization. All right. Now let's talk about the magnetic property of the Earth. Now I'm going to show you in a short how the magnetic property of the Earth is. But quickly, let me just define two major concepts that you could be asked in the exam It's called the angle of inclination, or we have angle of inclination and angle of declination. Angle of declination. We call it angle of declination or angle of dip. Angle of declination. Now, you know that we said when you suspend, I was supposed to give you this diagram. If you suspend a bar magnet like this to suspend it freely, it will come to rest like this. It will come to rest like this, roughly north, not roughly south. So if north is always facing here, it means that our geographic north pole, magnetic property of Earth, Earth's magnet, Earth's magnetic property. So it means if you suspend, we said that if you suspend, or it was found out also, if you suspend a bar magnet like this, to come to rest and roughly northeast direction. It means that if this north, since according to our rule, we know that unlike poles attract, like poles repel. So it means that North Pole is attracted to an unlike pole, which is the Earth's magnetic south. So the Earth's geographic north is the Earth's magnetic south. Does that make sense? The Earth's geographic north is the Earth's magnetic pole, magnetic south, and vice versa. The Earth's geographic south with the Earth's geographic magnetic north. All right. So, but the reason why it is coming to rest in this direction is this. If you place a compass needle on the magnetic field of the Earth, the magnetic field of the Earth has a magnetic meridian. So the magnetic needle will show north as roughly north, not as exact north. It will read north as there's a variation. That's why it's also called angle of variation. Do you understand? It's also called angle of variation. So that is there will be a difference between the Earth's magnetic field and the north that the magnet is reading. So, and that difference between those two is called the angle of declination. Is that okay? While there's something called angle of inclination. So this one is the difference between the magnets and the magnetic meridian of the magnet. That's the middle of the magnet, and the horizontal. So we call this one angle of inclination. We call that angle of declination. All right, that'll be it for this video. In the next video, we are going to be talking about the magnetic hand rules. So we're going to learn the hand rules, and we are going to also go into electromagnets and motor effect of electricity and generator effect. All right, see you there. Do well to like and subscribe to this channel. God bless you. And share the video with your friends.